Let's continue with sketchy history of quantum mechanics, or really the interpretation and philosophy of quantum mechanics. In 1900, that's really the start of the subject, Planck came up with a model to explain a very puzzling thing about how hot objects radiate. They just didn't seem to have the right kind of spectrum. And he posited that energy can't be subdivided arbitrarily in a completely continuous fashion. It must come in lumps that he christened quanta. And he gets a lot of credit for starting the ideas of quantum mechanics. But it was a long time before it was realized that this was the start of a complete revolution in physics. 1905, Einstein, who never really liked a lot of the aspects of quantum mechanics, but he helped to invent it, he discovered that the only way to make sense of what's called the photoelectric effect was, again, to assume that light must be quantized. So Planck said energy must be quantized, at least in some situations, and Einstein said, well, when an electric material produces light in a certain way by the photoelectric effect, he said the only way I can explain these experiments is that it must be happening in a quantized fashion, in a discrete fashion. And that's what got him his Nobel Prize, not relativity. At least that's what they named in the award. And it was the start of a very interesting period of ferment of how can you make that make sense. And it just seemed to be so foreign to classical physics. And in fact, it was, and it required a completely new physics. So quantum there just means lumps of something. It has a lot of different connotations now because of how all-encompassing the theory had to change. From 1900 to about 1910, people start discovering lots and lots of seeming paradoxes about the incompatibility of these ideas with classical physics. One thing that's amusing is that not too long before, Lord Kelvin had said, I can't remember the exact quote, and I think he's misquoted quite often, but here I'll misquote him again, basically saying that he thought that physics was done except for just kind of clearing up the decimal points and making everything more precise. He couldn't have been more wrong. That it was in fact about to change. That was in the late 19th century, and in just very few years, everything had been turned upside down. And the crucial years, for 1926 to 1928, a lot of interesting stuff happened in between, but in 1926 to 1928, there were sort of three fundamental figures that go into modern quantum mechanics. Schrödinger introduced what's called wave mechanics, which posited, again, that the electron is a kind of a wave, but it behaves in a way that you can see how particle behavior would come out of it. Heisenberg had what he called matrix mechanics, which introduced the idea of a state in the modern quantum mechanical fashion, like what I was calling X plus a state of the electron, for example. And the matrix nature of this is where linear algebra was first seen to come in. And then pretty soon after that, people realized that these were two ways to describe the same phenomena. And then someone who doesn't get mentioned as much, Born, is a really fundamental figure. He was one of the first people to emphasize that the wave, what this wave was actually measuring, was actually a probability, and that probabilities come into quantum mechanics in an utterly fundamental way. Other people realize that, but he gets the biggest credit for stating it in a very clear way. So if you combine these two pictures, you can see how they're really aspects of one unified picture. And then combine it with the probability interpretation of Born, you've got really modern quantum mechanics, not in its complete form, but pretty well. But it was weird. It was very, very weird. And people needed to figure out how do we interpret these results? What's really going on? What does this say about the nature of reality? It was clear what it predicted for experiments most of the time, as long as you could do the calculations. But it had very weird implications for what we think of as reality. The most famous interpretation came along pretty early in the 1930s, the Copenhagen interpretation, mainly due to Niels Bohr. And that had a lot of unpleasant features, and they're still unpleasant to this day, even though it's used as kind of the default, because in some ways it's maybe easiest to understand. It's not easy to understand because quantum mechanics is so mysterious, but maybe a lot of people find it easier. I'm going to talk about what's really an alternative to the Copenhagen interpretation. And it starts off from the 1930s. Two mathematicians, Birkhoff and von Neumann, they resolved to put quantum mechanics on a firm footing and to understand some of the weirdness of it. And there's three elements of their approach. One is that they talked about the fundamental idea of a measurement. That some experiment is done and you make a measurement of it, and that's supposed to be some well-defined process that happens. And it's been, ever since then, it's been difficult to resolve what is a measurement, how does that work, and there's this thing called the measurement problem in the foundations of quantum mechanics that's kind of led to. So that's not incredibly satisfactory. It was a big advance philosophically, but it's led to some real problems. Another thing that has been led to real problems, but was an advance when it came on, was the idea of the wave function, the collapse of the wave function. That roughly, this was basically something that's in the Copenhagen interpretation as well, but it shows up basically in Birkhoff and von Neumann's more careful work, that you have a fundamentally probabilistic object called the wave function, and then at some point, namely when there's a measurement, it collapses to have a definite answer. But the question of when that collapse happens, how that collapse happens, is it a physical process? Is it what causes it? Does it happen at all? Is it a fiction? Does it have something to do with consciousness or observers or people or humans? There's a lot of weird issues there. Okay. The neatest thing, I think, that Birkhoff and von Neumann introduced was the idea. They realized that if you want to make sense of quantum mechanics, it seems to inexorably lead us to redoing the foundations of logic. And the rules of logic, which we've got from the Greeks and then more elaborated by people in the 19th century like De Morgan and Boole, they just seem to not apply. They had a different way of redoing quantum logic from what I'm going to be talking about here. When I say, like I've already said, that in some situations you can't make sense of the statement A and B, if A and B are incompatible properties. They had a way to make sense of it, but they had to totally redo the laws of logic. It's very elegant mathematically, but the practitioners in this field pretty much seem to universally say that if the goal is to have an interpretation, namely something that makes sense to us in terms of how to describe reality, it's really not clear how to do that because it's too different from ordinary logic. And so what I'm going to be presenting toward the end here, and the idea of the consistent histories approach, just in a very schematic way, is an alternative that really comes out of this idea of quantum logic, but it's an alternative to throwing away the rules of logic, but it's going to throw away some things that are intuitive, unfortunately. So here's something that's due to Bohr and other folks around that time, the correspondence principle, that is really crucial, and that is that quantum mechanics must recover classical physics where it's accurate. They're not two separate theories. The world really is supposed to be ruled by quantum mechanics. It's just that if you apply quantum mechanics carefully to the systems that we already knew how to analyze with classical mechanics, you should get the classical answers because those experiments weren't wrong. They're not invalidated. So roughly, intuitively, it was understood pretty early on what that means, and usually stated in terms of scale, that large macroscopic objects are described by classical physics. So therefore, if you applied quantum mechanics to them, which tends to be hard, you should get classical answers. But if you have very small objects like electrons and photons and things in the Large Hadron Collider, then you are going to get very non-classical answers. And Planck's constant, fundamental constant of nature that goes all the way back to Planck in 1900, it turns out to measure that scale of when must you start using quantum mechanics. So that's sort of the early interpretation of it, and I'll modify that in a second. I do want to mention Feynman. When he reformulated quantum field theory in the early days to make it useful, a huge breakthrough, he actually kind of reformulated all of quantum mechanics to a certain degree. And he's got a beautiful explanation, a beautiful way of thinking about quantum phenomena that's great for intuition, great for calculation. It's not quite fundamental enough to be something that I want to talk about in this talk. If you can find another talk, maybe I'll do one of my talks about Feynman stuff. But if you want to look at his approach, that is a very, very good way to think about quantum mechanics at some level. But it doesn't resolve the absolutely fundamental paradoxes. And so, even though I mention it as a side issue and an incredibly important part of the history of quantum mechanics and how you relate it to classical mechanics, it's kind of a sidelight for this. Here's a little bit more of a modern take on the correspondence principle. I've mentioned the word decoherence already. The modern way to talk about this is that when phenomena get sort of complicated enough or interact in a certain way, you get what's called decoherence, and you get a systematic transition from quantum behavior to what can be described classically. So again, it's not that quantum mechanics stops working. It's that its answers are produced by they agree with what is a simpler system as classical physics. And it's not quite so much about the length scale as it used to be thought, but more about the kind of interactions within the system. This is becoming more and more crucial as people try to build quantum computers and try to create bigger and bigger and more complicated systems that are still coherent, that are described by quantum mechanics and have the weirdness about quantum mechanics, because that's essential for quantum computing. And I'll talk about that a little bit more in a later part of this series. It has to do, I won't say too much about this, but it turns out to have a lot to do with what's called irreversibility. It's a thermodynamic concept that has to do with entropy and the interactions of systems of particles. And so roughly it's that when you have too many strong interactions within your system or between your system and the outside world, you're going to lose quantum coherence and you're going to see classical physics come out. And in particular, if you're building a quantum computer, that's a bad thing. So we've got the good aspect that decoherence recovers classical physics, which is simpler and better known. And we need it to do that, or else quantum mechanics can't really be true. But the bad is that it destroys cool quantum effects. And those effects can be very cool. And if you watch some videos, I haven't created any yet, on quantum computing, you'll get a sense of that. Okay. So just to end this little section of the videos, there's a lot of work about this exact idea. Very, very practical work. Physicists are exploring the boundary between quantum and classical right now as we speak. And they're understanding and measuring the precise nature and amount of decoherence. So when I talk about decoherence in a philosophical context, you should be aware that it has a very, very practical meaning as well now. And there's even quantitative measures of what we mean by decoherence, the transition between quantum and classical. In the next video, we'll start working on some paradoxes and think about what's weird about them and a little bit about how to make them make a little bit of sense.